few things about massive gravity. There's been quite a lot of interest in massive gravity in the context of generalizing general relativity in 4 dimensions, and the motivation there is mostly to do with cosmological implications, because obviously if the graviton has a small mass, that's going to have implications at large distances. That ties in a little bit with the 3-dimensional. What I'm going to tell you about is essentially a bit of a different story. Massive gravity in 3 dimensions, and the motivations are rather different. We're not interested, obviously, in cosmology. We're essentially, the interest is largely in holography. So the basis for all kind of attempts to consider masses in the context of general relativity, the idea goes back to Fierz and Pauli. So I first want to tell you a few things about that. So Fierz and Pauli essentially wrote down equations for massive fields, symmetric tensors of arbitrary rank that describe, when quantized, would describe a particle of spin S. And that was in the context of 4 dimensions. You can do it in general dimensions. I'll think of it for the moment in 4 or 3 dimensions. I'm going to concentrate in a moment in 3 dimensions. But essentially their equations are, so we have mu1 to mu s, and this is symmetric and traceless. So you have one dynamical equation, and then you have subsidiary conditions. So in the case of s equals 1, basically we'd be writing down the Procher equation. And so from the Procher equation, there's original equation. You can derive these 2 equations, and then this one is the subsidiary condition. And in the case that the mass is equal to 0, that's the mass, then you could impose that as a gauge condition. In the massive case, you get it out as a subsidiary condition. So those are the Pauli-Fierz equations of spin S. And there's a feature in 3 dimensions, is that these equations factorize. Because if you count the number of degrees of freedom here contained in this, that's d into d plus 1. Well, you could count up the number of degrees of freedom in that, and you subtract the number of degrees of freedom due to the subsidiary condition. You get basically an irreducible representation of the rotation group in d dimensions, except in the case of d equals 3. D equals 3, you get basically 2 representations. In fact, it's always just, the answer is the number of independent components is always 2. And that's built into the fact that you can factorize this equation. So what happens is that, so let me just define some quantity here, h mu1 mu s, mu1 mu s, epsilon tensor mu1 mu1 mu2 mu2 mu s, symmetrized all of those indices, and there's a free index there, d tau, so that's a first order differential operator. So if you consider this first order differential operator, these are second order equations, apart from this one of course, then you find that using that first order differential operator, you can rewrite those equations as so the FP equations are h minus sm, h plus sm, phi, I just write it schematically, equal to 0, and this in fact implies then the subsidiary condition. And these 2 commute, and basically the solutions are, this is either annihilated by this factor or is annihilated by that factor, and those 2 pieces propagate the 2 helicity. This is, H really stands for helicity here, they will propagate a mode of mass m and helicity s plus s in that case and minus s in the other case. So that's the factorization. And so you can generalize. There's an obvious generalization because essentially you're having two separate irreducible representations of the Poincare group are propagated by this second order equation. And it factors into two first order equations. You can clearly generalize to
you understand correctly that S actually drops out because H is proportional to S and then you have SM, so you might as well drop the S everywhere, or is it
well, I've normalized it. Let's see, I had a normalization, and now why did I choose my normalization? Probably so that the eigenvalue was precise. Well, actually, no. Well, that's to do with my convention for symmetrization would involve 1 over S's.
Okay.
I can't remember precisely what the convention was for normalization now, but that's not really going to be important here. So you can generalize this to two different masses. So essentially what's happening is you have two modes. Each one is propagated by each of these factors, and they have the same mass. And the reason they have the same mass is because they started with equations which were parity preserving. And essentially those two modes, the one with a positive helicity and the one with a negative helicity, are a parity doublet. But if you break parity, which you can do by adding some parity breaking term, then in principle you can split that degeneracy under parity, and then one propagates with one mass, call it m plus, and the other propagates with the other mass, m minus. And so you would have this kind of equation. Again, that would imply the subsidiary condition. Then, yeah.
So this is, you're talking about gravity, but these are
not gravity yet.
These are so far equations on some flat.
Perhaps I should have prefaced, exactly. I should have prefaced what I'm saying, that basically what I'm going to try, essentially what I'm going to do is a subtitle of what I'm talking about could have been that from NMG to ZDG, but none of you would have known what those things mean, so I didn't say that. But the point is, this is basically gravity, high derivative gravity that is equivalent to interacting Fiat's-Pauli theory. So one of the basic problems, of course, the reason that Fiat's-Pauli is not much considered till recently was that the problem is that how do you introduce interactions? And the typical problem that arises is that as soon as you introduce interactions, you get ghosts or non-unitary theories and so on. So there's been a lot of work on this. That's all the stuff in this four-dimensional work recently on massive gravity has basically been trying to solve that problem. And it's very complicated, and I think I'm not very convinced by it. But in 3 dimensions, there's a very simple solution. And that's essentially what I'm heading towards now. I'm going to start with Fiat's-Pauli, and I'm going to derive for you this theory here. Then I'm going to explain the problems. Then I'm going to explain essentially the relation of this to holography and an essential problem that appears in all massive gravity theories in 3 dimensions, which is clash between bulk and boundary unitarity. And then I'm going to tell you how those problems are resolved by kind of new model. Perhaps I should have started with that. But I just kicked off with the Fiat's-Pauli. It's quite true that the Fiat's-Pauli doesn't involve any gauge theory. We're not talking about gravity yet. But if you bear with me just 2 minutes, then gravity will appear in just a moment. So the point here is that we can take the limit of m minus goes to infinity for fixed m plus, call it equal to m. And then this gives just a first order equation. So you have h minus sm phi is equal to 0. And that just propagates a single mode of spin s. Now, what I want to do now is to focus on well, first of all, let me just, I was in fact doing the case of general s, not because I'm interested in going to s equals 3 or something, but I also want to illustrate things with the simple case of s equals 1. as everybody knows. So let's just take the case S equals 1. Point then is you have H minus M. So you get this equation, and that implies a subsidiary condition, as I said, which in fact in this case is just a vector field equal to 0.
Can I ask a silly question?
Yeah?
S equals 0 is somehow excluded from consideration.
Yes. I'm excluding S equals 0. It has it's rather different, yeah. As I'll come to later on. It's also different in the case of holography and so on. So, yeah. So basically what I'm describing here could be said to be, you see, the square root of Prof. It's a first order equation. It propagates only a single spin 1 mode. And basically the equation implies the usual subsidiary condition. But it's only first order. The usual Prof equation is second order, basically taking a kind of square root of that. Now, the point now is that if you look at this condition, that's just saying that a vector, we're in 3 dimensions, so that's just saying that this vector field here is divergence free, which means it can be written as a curl. So
between the left side of the board and the right side of the board, the M just drops out? The mass doesn't appear in your divergence-free condition?
No, that's right. That's right. So, for example, yeah, exactly. So it doesn't also in the Proker. I mean, you've got an equation that involves the mass. You take the derivative.
Yeah.
That's right.
Oh, you said it implies this is not necessarily equivalent to it.
No, it's not equivalent. No, it's just it implies. The point is there are essentially 2 equations. So it's a dynamical equation, and if you have a mass, then there's the subsidiary conditions, which are needed to remove all the extra modes. As up there. Now, the point is, you can once you write the equations a certain way, then those subsidiary conditions are implied. So that's what I'm saying here. This actually is in a form that implies the subsidiary condition. What I want to do, though, is just to solve this condition. So that says it's divergence free, so it has to be written as a curl locally, and so you solve it. You solve d mu phi mu equals 0. That tells you that phi mu is equal to introduce another field f dA, so you have another vector potential, and I can simply write that as the curl of that other vector potential. And if you substitute, then you end up with the equations. You substitute it into the other equations, so you end up with f rho sigma. You end up with this equation. It only involves field strengths, but actually propagates a single particle of mass m. If you work on that a little bit, you'll find that that's the case. That's actually a theory that usually goes by the name of topologically massive electrodynamics. So basically what you do is if you take Maxwell Lagrangian and you add to it a Chern-Simons term, which is gauge invariant, then you vary, you get this equation. That's topologically massive electrodynamics. Now, if you do exactly the same thing for spin 2, this is what happens. So now if you look for spin 2, well, in that case you have this H minus 2m phi equals 0, and that implies the subsidiary condition, which is this one here. And so this is, let me call that the square root of Fiat-Pauli, because when we say Fiat-Pauli, we usually mean spin 2. So if now you solve that, you solve the subsidiary condition, what you get is that phi mu nu is equal to 1/2 epsilon mu tau rho epsilon mu lambda sigma. Now it's second order differential operator on another field exactly of the same index structure, symmetric tensor. And it turns out that this is actually nothing else than the linearized Einstein tensor. Just as that was the field strength for a spin 1, essentially what you end up here is call it a field strength, if you like, for spin 2. In fact, it's the Einstein tensor. And if you simply substitute, then in fact you can use the fact that this operator acting on this is proportional to the cotton tensor. So that's the, I should say, the cotton tensor, which is the analog of the Weil tensor in 3 dimensions. And so you can see that, so if you use that, you can see this term here, that just becomes the, you get an equation G mu nu plus 1 over m squared C mu nu. Factors work out appropriately. You get essentially this is equal to 0. Of course, what you get is this linearized. But at that point, you see this. So that's completely equivalent to this square root of Fiat's-Pauli by construction. But it's manifest now how you introduce interactions into this. Of course, it's the square root of Fiat's-Pauli, but not quite as good as Fiat's-Pauli, but yeah.
So very basic, probably. You're in Minkowski space.
In Minkowski space at the moment.
So where does your cotton tensor is virtual? I mean, it's 0. Is it a cotton tensor of the metric or what?
No, this is it's well, this is the equation. I mean, if C mu nu, if the equation were that C mu nu equals 0, yeah, at the moment I should say that I'm looking at this is linear. This is yeah. So you mean what I'm doing is doing Fiat's-Pauli, right? And I'm showing the square root of Fiat's-Pauli, and I'm showing that actually equivalent to this. This is a linearized tensor, right? So this is just linearization. So I take the, if you like, take the cotton tensor, plug in G is equal to Minkowski plus metric perturbation, and then treat this, view that as the metric perturbation. So this would be what you get from that expansion. But so the point now is it's completely clear how you introduce interactions here. You just simply remove this lin here, and then you have a nonlinear version of that, which manifestly, if you expand about Minkowski space, describes exactly the content of this square root of Fiat's-Pauli, which is one mode of spin 2. And that's, of course, a well-known fact, because this is a well-known theory. This is known as topologically massive gravity, which was introduced long ago by Dessler and Jaquib. So that's a derivation of topologically massive gravity. And in fact, it's a proof at the same time that when expanded about Minkowski space, it propagates a single mode of spin 2.
Doesn't the cotton tensor have 3 indices?
Pardon?
Doesn't the cotton tensor have 3 indices?
No. Only has 2.
It does. This is the Hodge dual.
Cotton tensor only has 2, but
Interesting.
I don't know, maybe you're thinking of some other tensor.
Is the solution most general and if locally that solution?
Say again?
The solution is general solution.
I don't get it, sorry.
The solution is given.
Oh, the solution, sorry. Yeah, that's a general solution. I mean, the general solution locally. Locally, it's, sorry, yeah, the general solution. Just like here, I mean, divergence reads a curl locally, that's general solution. So this is locally. So if we're only interested in degrees, I'm only talking about degrees of freedom. I'm constructing this, constructed in such a way that it propagates those degrees of freedom. Now what I want to say is that what happens, and that's why I'm focusing on this particular theory. I'm talking about massive gravity in 3 dimensions. There are various massive gravity theories in AdS. All I have to do, put this in AdS, is I just add a cosmological constant. I'm going to do that in a moment. But I don't want to talk about topologically massive gravity theory because I just want to focus on the other one. I want to focus on the new massive gravity. And you can construct that as follows. What you do is instead of taking Fiat's-Pauli, instead of taking the square root, you take Fiat's-Pauli itself. And so you simply apply the same trick to second order Fiat's-Pauli equations.
Paul, sorry,
Yeah.
just one last time.
Yeah.
So do you now, having non-linearized it, do you now insist that these equations on top, this divergence-free condition, that it still holds for a curved metric? You replace this partial derivative with a covariant derivative.
Well, Let's see. I mean, I'm not quite sure what the question's getting at. I can expand about different backgrounds. Right?
If you were, so the question is, does the equation on the right corner of the first blackboard still hold for the curved metric?
Oh, well, that's, no, I mean, see, there's not, a subsidiary condition, you mean?
That's right.
That's gone. I mean, I solved it, right? I solved it. I got you some linearized equations, which by construction, they're completely by construction. They are the same as the Fiat-Pauli equations.
So now when you...
And now I say, but those equations, I can immediately make them nonlinear.
But now there is some curved metric which appears in this.
I mean, essentially, it's the Bianchi density, right? What's happened is that the subsidiary condition has now become the Bianchi density. And so there's it became the linearized Bianchi density, but now I introduce the interactions, it becomes the full Bianchi density.
Well, you see, but if you did have an equation like that on the curved background, then you would be in trouble because...
Well, you would be, and indeed, that's precisely the difficulty with
because you would commute the derivatives and you would obtain some constraints on initial data.
You would be in trouble. That's right. That's why we're not doing it that way. In other words, if you just try to say, let's try to introduce interactions directly into the Fiat-Pauli, you run into difficulties, and that was a problem that nobody solved. That's why Fiat-Pauli was done in 28 or something, and nothing happened for 60 years. Well, a lot more than 60, right? Because you immediately run into problems and you don't know how to solve them. Now, in the case of 4 dimensions, it turns out, well, I'm not going to discuss all the recent stuff about that in the context of 4 dimensions. The thing is, in 3 dimensions, there is a very simple solution. And the solution is, you just get rid of that subsidiary condition at the very beginning by solving it. Now it's gone. Now it becomes a Bianchi identity, and you've got gauge theories, and now you know it's trivial how to introduce interactions. And your subsidiary condition became a Bianchi identity, that becomes a nonlinear Bianchi identity, and there's no problem whatsoever. The whole theory is consistent. Now, of course, I've only shown for you that it actually propagates, what it propagates. The way it's constructed only guarantees that in that Minkowski background, it propagates what I told you it propagates in the beginning, a single spin 2 mode. And you can ask, what about other backgrounds or the ghost, etc.? Good questions, to which I'm going to give you the answer. But not for this model, because we already know the answers for that. So the point is that you can apply the same trick to the second order Fiat-Pauli equations. And then what you get is, you see, you get this on the, well, you get linearized because, yes, on the Einstein tensor now, linearized, and then the other subsidiary condition, the subsidiary condition is gone, but there is the condition of tracelessness. I mean, I said up here, the general case, it's traceless, right? So for spin 1, that's not a condition, but you have to take into account the tracelessness. So the tracelessness essentially tells you trace of Einstein is 0, which is the same as the Ricci scalar is equal to 0. Well, that's just linearized. So, well, it's not immediately clear, in fact, how you make all this nonlinear. But let me just say that these equations, these 2 equations, are equivalent to the one equation, which is G mu nu linearized minus 1 over n squared box. G mu nu linearized minus a quarter. Actually equivalent to a single equation here, because if you take the trace of that, this is traceless by definition, then that tells you that, hold on, yeah, that's right, so if you take the trace,
yeah, it's there.
Okay, well,
Yeah.
For some reason I don't see what I'm talking about right now, but I'm sure it's true. And the point is that you get this, and you can easily see that it's clear that this comes from the Einstein-Hilbert action, quadratic version of the Einstein-Hilbert, because it's linearized here. This comes from something which is clearly 4th order in derivatives. So you're looking for some quadratic term in the coaches. And, well, you can just write down the general thing, look at the quadratic expansion and see what happens. And indeed, you get this from from the following Lagrangian. and this k is r mu nu squared minus 3/8 of r squared. Seemingly strange combination. Now let me just say a few words about that. Of course, there's a linear. You get that from the linearization. You take the quadratic approximation of that, and that produces. You vary it, and you produce this. So that immediately, therefore, you can generalize it to an interacting theory, which is this. So this is in fact the new massive gravity as it was first found in that particular form. It comes in with this funny combination, which I'll explain why that combination appears in a moment. But let me just say a few things here. First of all, I put a minus sign in here, not because I want you to take notice of precisely what my conventions are, and I'm being very careful about those conventions, but the point is that's the wrong sign, right? So the point is it's the opposite sign to what you get in general relativity. Whatever your conventions were, then you just change the sign. And that's essential because, in fact, if you there are two things that could go wrong. You see, if I expand about Minkowski space, just restricting for that for a moment, there are two things that could go wrong. You could have ghosts, you could have tachyons. Now, if you don't want tachyons, then you're going to have to get the relative sign right here, because that affects the equation, and so the relative sign has to be exactly as I've written it. Of course, it has to be to give this. You also need the overall sign, which of course is not determined by the equation, but you need that in order to avoid ghosts. So if you look to see the kinetic terms, they have to come out positive. The energy has to come out positive. And so you need the overall sign. The overall sign then fixes that to be the wrong sign relative to the... That's the same, by the way, in the case of topologically massive gravity. It's a feature of all of these massive gravity theories, and it has consequences, which I will come to later. Now, the point is here, it's by construction that model will propagate two massive spin 2 modes and a parity doublet. Notice that it preserves parity, and that's the reason why both the modes are ghosts or not ghosts. So if I do the same trick for Proker theory, then you get a higher order theory for electrodynamics, but what happens is it always propagates a ghost. One of the two spin 1 modes is a ghost. In the case of spin 2, then as long as you choose the overall sign correctly, both modes are physical.
Is there a simple way to explain the difference? I mean, it's just why is spin 1 and 2 just so different?
Yes, because if you construct the action in this case for the Proker, you discover that in fact it breaks its parity odd. The action flips under parity. But in fact, it's an even versus odd spin. All odd spins will give you an odd parity action, and one of the modes will be a ghost. If in the even spin case, spin 2, then they will not be ghosts. So you don't get ghosts precisely for spin 2, but you do for spin 1. So now we're in the realm of gravity. Let me just say that there's an equivalent action is so you can introduce an auxiliary field, auxiliary tensor field, auxiliary symmetric tensor. And strangely, in fact, you get exactly the Fiat-Pauli mass term for that field, and that's crucial. In fact, if you vary f, so if you take the action and vary with respect to f mu equals 0, that tells you that the f mu is the Skelton tensor. Now, that implies that, of course, that basically tells you that that k is proportional to g mu nu s mu nu. And this is a combination, actually, which has very special properties in all dimensions. For example, in 4 dimensions, it's equivalent to the Weil squared term. In high dimensions, it's Weil squared plus Lovelock and so on. So it always has very special properties. But so this basically linearizes it. Now we've got second order equations coming from here, and you can, if you're expanding about some background, that's a useful thing to have. So it's essentially an equivalent version where I introduce an auxiliary tensor. Now, of course, I can add the cosmological constant, and then I get L is equal to G. Now, for the purpose of adding a cosmological constant, call it lambda 0. It's actually a cosmological, I should call it cosmological parameter rather than a constant. I mean, it is a constant, but it's not the cosmological constant. I've introduced here a sign, sigma is equal to plus or minus 1. Just because it's nice to have the sigma is minus 1, of course. The wrong sign means minus 1, but for the moment it's useful to allow for the other sign temporarily. Now, if you seek, the idea now is that you seek maximally symmetric vacua. And that means that G mu nu is equal to minus lambda G mu nu, little g mu nu. And then this is the cosmological constant here. By definition, and then lambda will equal to minus 1 over L squared for AdS. Now, that's not the same as the constant lambda 0 that appears up there when you have this extra term. In fact, the relation between them so the relation between them, in fact, is you get that sigma lambda minus lambda 0 plus 1 over m squared lambda squared equals 0. And that tells you that lambda is, in fact, minus 2m squared sigma plus or minus an a of 1 plus lambda 0 over m squared. So that's the relation between the cosmological parameter and the actual cosmological constant. But now what we do is we simply say, okay, let's expand. We know the answer is, we know actually expanding this about Minkowski space, it's already by construction, we already know exactly what's propagating. But let's now try expand it about some other maximally symmetric background. So if you expand, yeah?
But lost, what is S mu nu?
S mu nu is the Skelton tensor. Now, I didn't tell you what the Skelton tensor was, but you want me to tell you what Skelton tensor is?
Just to...
Let's see. The Skelton tensor, as I like to say, is is the tensor of most significance that you've never heard of. Right? So the Skelton tensor, it's in 3 dimensions. It's dimension dependent, actually. But in 3 dimensions, it's r mu nu minus a quarter g mu nu r. The Cotton tensor is basically the curl of the Skelton tensor. That's the it's the Skelton tensor always appears in anything to do with conformal gravity. Skelton will always be there. You know, so in any dimension, in fact. So, but in 3 dimensions, that's what it is.
There seems to be a special point. Lambda 0 can be negative, I suppose.
Yeah, it can be. That's right. Well, obviously not too negative. Clearly, otherwise there's no solutions here, right? Yeah. There are very special things that happen when that's precisely equal to 0, but they won't be relevant for AdS because that will never happen in the unitary theory in AdS. So the point now is I'm expanding. Basically, I'll expand it in this form where they have a G and an F about a vacuum, about some vacuum G bar which has a cosmological constant lambda. And then there's a particular, well, you see, you choose a basis. You expand, but at the same time, I make a change of basis. So there's G mu nu is equal to G mu nu bar of lambda plus, and then there's an H mu nu. I put this in now because I want to stress that it doesn't work for a particular choice. So essentially, I have a basis of fields here, which I pick out to expand in, which are this K. I've basically replaced an F by a K, and then I have a metric perturbation. Little h as usual, and if you do that, the point is that you end up with something that's quadratic. And so this gives you a quadratic action then is equal to sigma minus lambda over 2m squared, the Einstein-Hilbert in terms of that h, and then plus you have 4 over m squared, lambda minus 2m squared sigma. And then you have Fiat-Pauli for the k, and with a particular mass, m, and m squared turns out to be, I haven't told you exactly what Fiat-Pauli is and ended as it, but that will appear in a moment or two. So, but basically you do an expansion, this particular expansion diagonalizes at the same time. So if you focus on that, you can see that you can immediately read off the various, immediately read off some things from here. First of all, the point is that in 3 dimensions, precisely in 3 dimensions, the Einstein-Hilbert term doesn't propagate anything. So you would say, well, that's completely irrelevant, this term here. We won't worry about that. But here's the Fiat-Pauli term. That's propagating the 2 spin 2 modes. Now in AdS, or in fact, it could be de Sitter here too. But of course, you see that there's a coefficient in front, and that better be positive. And you also see the mass term, well, that better be, m squared better be positive too, in order to avoid tachyons. So you can immediately read off the conditions to avoid tachyons, the condition to avoid ghosts, as far as the bulk is concerned. And those 2 conditions, if I write here no tachyon, no ghost,
Or can you allow tiny tachyons?
Good question. In fact, the answer is yes. I mean, well, probably you're asking, if I may reinterpret your question, you may be asking, what's the Breitner-Friedman bound for spin 2? And the answer is there isn't one. Or rather, there is, but it's trivial. It has to be positive. M squared is positive. Strictly positive, yeah. Or 0, super. So that's the bound. So you can work out the unitarity bound for any spin. It turns out that precisely the spin 0 case is very different from from spin non-zero, essentially because then you have this Breitner-Friedman bound. M squared could be negative, but so that doesn't arise. And so what you require is that you see that you require 2 things. So no tachyons. Whoops. If you require now no tachyons, and you require no ghosts, then you can see that requires m squared greater than 0. Well, I should say implies. I mean, m squared, it's because it's perturbative. And it also implies that lambda has to be greater than 2m squared sigma. So you immediately read off those 2 conditions. And by the way, this is for lambda less than 0. And to de Sitter, this tells you that sigma has to be minus 1. So less than or equal to 0. So as in the Minkowski space, you'd have to choose that wrong sign term for the kinetic term, for the Einstein-Hilbert term. That's the bulk. So this is the bulk. So this is basically what you want for bulk unitarity. Not quite sufficient, because you could worry about that other degrees of freedom would emerge in other kinds of backgrounds. So you have to do a non-perturbative check later to show there are no other degrees of freedom in this theory. But that can be done, and you can show that there are no other degrees of freedom. Now,
Sorry, Paul.
yeah?
So can you actually get a massless spin 2 field propagating this 3-dimensional space?
Massless. Well, no, not really. Well, in some technically yes, but that's a special case. That's critical gravity, which I'm going to come to. I'll make that point. I should have made a point here because I wrote this out rather explicitly because you notice that it involves lambda 1 over lambda minus 2m squared sigma. So you see, I'm assuming here that lambda is not equal to 2m squared sigma. And you see that in fact is the limit at the unitarity bound. So that case has to be considered specially. So right now what I'm doing is I'm doing everything except excluding precisely when this bound is saturated. And I then have to go back and tell you, well, what happens when that bound is saturated? And in fact, that is precisely the case when m squared is equal to 0 here. We're on that bound. So maybe that was the point of your question. Yeah, so I'll come back to that in a moment. The answer is, well, yes, but it's not unitary. The bound, actually, to get unitary is turns out, it's strictly greater than. Now, if you look at the other term in here, you see, we threw that away because you said, well, that doesn't propagate any modes. But it turns out that coefficient is also very important because in the context, for various reasons, for example, in three-dimensional entity, you have BTZ black holes. And if you work out the mass of those black holes, it turns out those mass is proportional to this factor in front here. Also, if you look at it in the context of the AdS CFT, then if you use the Heno-Brown calculation to work out what the corresponding central charge is, of course, that's assuming that it's going to be large in order to justify the semi-classical approximation here, then it turns out it's this coefficient here, up to a factor. So in fact, the L2 Einstein-Hilbert that doesn't propagate modes, but the coefficient, its coefficient determines the central charge of the boundary CFT. And in fact, what you get is that C is equal to, there's a factor out in front which involves the radius of curvature AdS and the Newton's, three-dimensional Newton's constant, and then it's exactly that factor which appears in there, which is sigma minus lambda over 2m squared. And now you see the basic problem which besets all of these three-dimensional massive gravity theories, including, as I say, all the other theories that people have considered up to now, except for ZDG, which I'll come to later if I get the chance. But the point now is that this, you see, will be less than or equal to 0. In fact, it will be less than 0 when lambda is greater than 2m squared sigma. So immediately what you see is there is a clash between the bulk unitarity requires lambda greater than 2m squared sigma, but boundary unitarity requires lambda less than 2m squared sigma. Of course, there's this special case right in the middle, right? And you'd say, it's okay, what happens when it's exactly equal to 0? We'd have to look at that case. But so there's basically a clash between bulk and boundary unitarity. And I've exhibited that in this particular theory, but if you look at all, anybody else's favorite theory, exactly the same thing. After you've done all the dust has settled, you try do whatever you like, you find it's exactly when it's non-unitary in one, it becomes unitary in the other. So in the boundary. So there's a basic. Yeah.
That's a stupid question. Is it known what the unitarity in the CFT is dual to, in general?
Well, I mean, we don't know what not much is known about the CFT, right?
No, I mean, what having a unitary CFT requires you to have in the bulk?
Oh, yeah, it seems to require you to have a non-unitary theory in the bulk, according to this, right? That's the whole problem. But we don't believe. Well, of course, the thing is that one believes probably if you have non-unitarity in the bulk, then that will show up at some stage in the conformal theory, but not in the central charge. And in fact, as I recall, there's some paper, Kostas Skanderis wrote some paper illustrating that in the context of TMG, I think, actually. He was interested, I think he addressed that issue, as I recall. no doubt with some other co-authors whose names I can't remember. But yeah, so I think the situation, it's bad. Yeah, it's bad also for the CFT, but not immediately so. So I mean, it is essential to have a proper theory, a theory that's going to make sense as any kind of quantum theory of gravity. You have to solve this problem of boundary versus bulk unitarity. It's a basic clash in all these attempts to introduce massive gravity. And the attempts, as I say, I mean, are extremely, this theory is not arbitrary. You start with Fiat-Pauli and you basically derive it directly starting from Fiat-Pauli. I mean, I could have done the derivation, instead of in Minkowski space, I could have done that whole derivation directly in anti-de Sitter space right from the beginning. It just would have been more complicated.
Now, aren't we using unitarity? Well, I don't know if this translates into real unitarity of S matrices. Aren't we using this to solve Hawking information paradox, or is this?
I don't think I've solved any Hawking information paradox.
No, but the fact that unitarities left and boundary and bulk are.
It might be clearer if you comment that when you talk about CFT unitarity, here you just mean positivity of the central charge.
That's a necessary condition.
Right.
I mean, it's a necessary condition, right?
Right.
It's certainly not sufficient, and that's how I was trying to reply to the previous question. And in fact, it won't be sufficient. If the bulk theory is not unitary, then even if you have a central charge that's positive, your CFT will in fact also be non-unitary. It's just that you don't get to see that immediately.
And conversely, when you said bulk unitarity, you mean perturbative bulk unitarity.
And indeed I do, yes. Perturbative bulk
Issues that,
unitarity.
as you mentioned, just to remind everyone and clarify, you can see that there's an issue in the bulk for this other sign, because if you have if the central charge is negative, then your spectrum of BTZ black holes in the bulk is unbounded below. There's a natural.
Although the BTZ black holes, I'm not quite sure to what extent I call that bulk, because I think that's sort of should be viewed more as boundary actually. But
better definition. It's a feature you can see from the action you wrote down.
yeah, I mean they're not things you're going to create in pairs, and so I'm not sure I'd want to consider those as well. But okay, that's semantics perhaps. Yes, I mean there's a problem with the BTZ black holes, and it's essentially the same problem as the central charge. So there's that basic clash. Okay, now I could say a few words about this special case, but perhaps I won't, because I don't really have much time on that. And let me just say that you can go back and look at this special case. You look at the original fourth order equations. What you discover then is that essentially, as long as you're away from this unitarity limit, you get the same conclusions, that there's basically two sets of equations and exactly the same conclusions. What happens is essentially there are degeneracies occur in the fact the equations are all factorized, by the way. So it's a fourth order equation, you now get 4 factors. And the problem is that when 2 of those factors become the same, then it's a typical thing with differential equations. The initial indices are the same, or different by an integer, you start to get logarithmic solutions. So there's some issue it looks as though you're taking m squared equal to 0, but you don't get the standard kind of mass. You get kind of logarithmic modes. And then the boundary theory is supposedly a logarithmic conformal field theory. Although I don't actually see, since the central charge is going to 0, you don't, the semi-classical approximation is not justified as far as I can see.
Can you repeat why you're expecting a log CFT on the boundary? Just because it's non-unitary?
Well, as I say, I'm not sure why I should expect it, because the central charge has to, in order to justify the semi-classical approximation that the gravity is telling you anything about the boundary, the central charge has to be large, and we're putting it to 0. So, but nevertheless,
CFT, because if you compute the correlator in a log CFT, you find this addition.
but nevertheless, so I'm not quite sure how that's justified. But you'd have to put that to the people who have been writing all the papers about log CFTs in relation to critical gravity. So that's a whole relation to critical gravity, log CFTs, and so on, which I think I'll just skip. I just want to say a couple more things in the time I have left. And one is that there's a very nice reformulation of this. I haven't been given any names of people, have I? I should. Well, I'll maybe do that at the end. So there's a nice reformulation. There's a nice reformulation of this, which suggests something, and it ultimately suggests a possible solution to this problem that I've mentioned. And the point is as follows: that you can write it with is that it's well known that if you just take the Einstein-Hilbert term, you can view that as Chern-Simons theory. So you can rewrite it. In fact, well before that, I mean, you just Cartan, he rewrote general relativity in terms of essentially form language, and that's all you can do is you simply rewrite the whole thing in terms of forms. So and then in fact, I may call that. So let's start with the Einstein-Cartan for general relativity. This is basically a three-form Lagrangian, and so you have a dry bind. We're in 3 dimensions, and you have a corresponding curvature for a connection, and then you can add a cosmological constant in, and the whole thing can be written in terms of forms here. So essentially, you have 2 forms here, E, EA, and you have omega A. In replacing a metric and connection, you basically have those 2, and you view them as independent fields. And as is well known, that's completely equivalent to general relativity. Now, what you can also do is that for NMG, you can do something similar. You introduce 2 new fields, one of which, in fact, is essentially that F there. So I have an FA, which is basically a kind of form version of that symmetric tensor there. Now it has an antisymmetric part principle. And another one which is Lagrange multiplier term, which will be HA. And then you write down the following Lagrangian, which turns out to be completely equivalent. It's the Einstein-Cartan one, and then I have a Lagrange multiplier which tells me the torsion. So that's the torsion, that's the curvature 2 form. Here is the torsion. If you add this term to the Einstein-Cartan, it doesn't do anything. It's completely equivalent, actually. So you can just start by it. But on the other hand, if you're going to start adding other things, then you better have it there. So and then you simply replace all of that stuff up there. You simply replace by 1 over m squared FARA minus a half epsilon ABC EAFBFC. So it's remarkable that and it only works for this particular combination. So precisely for that combination that gives you ultimately that r mu squared minus 3/8 r squared, you can rewrite that without introducing a metric. So no metric here. It's just these forms. And what that does is that well, first of all, that simplifies the Hamiltonian formulation. So you can now use this in Hamiltonian formulation to prove that, in fact, there are no other degrees of freedom. No matter what background you solve about, the phase space is always physical phase space is always 4-dimensional, corresponding to 2 it's corresponding if you linearize about Minkowski space or something to degrees of freedom, propagating degrees of freedom. And this also suggests that there's some kind of limit here. Now you've got these 4 fields that suggest that perhaps these are some kind of limits of some second, you can think of this as some kind of second metric. Up there, you could have thought of it as some kind of, additional auxiliary metric.
So this field F, it has values in some, I mean, it's not a, it's not a one form, right?
Yeah, this is just an independent one form.
So why is this last term 0? I mean, you have, epsilon
This here?
That's right.
Yeah, there's a B. Yeah, no, I'm not writing the form indices. They're all vector valued forms. Lorentz vector valued forms, yeah. I'm not writing all the mu indices. Lorentz vector valued.
So we have some torsion here.
Yeah, well, the point is, well, there's a torsion of there's the dry bind here, there's the usual, formalism of Einstein-Cartan, and I'm just using that formalism and saying the extra term you add on, it can be written on without needing a metric. You don't need a metric to write it down, which is remarkable. It's the only combination for which you can write down without a metric. It's precisely the combination you need for this model. And it suggests that perhaps there's a version where you can view this as some kind of limit of a theory where you really have two dry binds and two spin connections. And that leads to Zwei dry bind gravity, which I have no time to tell you about. But let me just say that indeed it works. That this theory actually can be viewed as a limit of another theory which has two dry binds, two spin connections, only one general covariance and one Lorentz. But nevertheless, it limits to that, and so you can reobtain this new massive gravity theory in that way. But you get a theory with more parameters now. And if you look around in that parameter space, you find that indeed you can choose the parameters so that you get positive central charge and unitary propagation of spin 2 modes in the bulk. And so that's just, I just leave that as an advertisement for Zwei dry bind gravity, which of course the physical review didn't let us use. Because they say that you can't use the word Zwei. You can have dry bind, that's okay, because that comes with the bind, but you can't have Zwei. We said, yeah, but we want Zwei hyphen, it's all kind of, think of it as all one word. But then that's a new word, no, it has to be, you can't use that. So I don't have time to tell you about Zwei dry bind gravity. But the point, the message I basically want to leave is that that first of all, that massive gravity theories in 3 dimensions are rather natural. There is a solution to the problem of introducing interactions in Fiat-Pauli theory, and it leads naturally to this model NNG. That's one take-home message. The other one is that there's a basic problem in those theories between the boundary unit, the clash between boundary and bulk. It's not really a clash because ultimately it just means the theory is non-unitary. And how do you get around that problem? Indeed, is there a way around that problem? And the answer is yes. It seems that there is in the context of the Zwei dry bind gravity. By the way, people in 4 dimensions have a Zwei fear bind gravity. Because everything you can do in 3, you can try to do in 4.
Do they publish that in the physical review?
No, I think not. But the whole motivation, a lot of things are very different. In the 4-dimensional case, what happens is that there you have to worry about, solar system tests, for example. If the graviton is massive, there's an old problem in the past. How can the graviton be massive? Because it affects the deflection of light by the sun by a factor of 2 or something. So it's clearly ruled out. That turns out to be a completely spurious argument. Essentially, any theory, what will happen is that at sufficient, you can essentially tune the parameters such that you recover general relativity at a distance below some particular scale, called the Weinstein radius. So below that scale, you only see the 2 degrees of freedom of gravity. Gravity looks like general relativity. So it's only when you go out, you just pick that scale to be larger than the solar system, and immediately no problem with solar system tests. So in principle, then of course, but the theory looks ugly because you've broken general covariance. But then you restore general covariance, but that introduces a massless graviton. But then you pick the Planck mass to make that massless graviton only apparent at scales beyond the cosmological horizon. So you're never going to see it, even though you have a generally covariant theory. So you just have this massive graviton effectively for cosmological purposes, and within the solar system scales, it reduces to general relativity. So that's the basic idea of how the 4-dimensional massive gravity people want you. That's the pitch that they would pitch to you. Personally, I don't believe a word, but that's. Oh, I shouldn't have said that, should I? I'm on camera. Please scratch that last remark. I've run over time, so.
You're done. Thank you.
What if you write the Einstein-Cartan using SL2R cos SL2R Chern-Simon theory? Can you couple it to something else in here with F and H?
Well, yeah, I mean, that's right. It's rewriting, isn't it? Taking linear combinations.
Yeah, but then it's coupled to something else, right?
Well, you could, well, you could ask the question about coupling. I'm not really coupling anything here, right? This is, this is essentially just a way of rewriting curvature squared terms.
You know, of course, but
Yeah.
we introduce F and H, right? And
Yeah,
we write
yeah.
E plus omega and E minus omega as
Yeah,
F.
well, yeah, one's an auxiliary field, the other is a Lagrange multiplier. It's not exactly what I would call coupling to matter. You could rewrite things that would look probably a bit more complicated. Maybe it looks simpler, but I'm not sure. But coupling to matter, well, I presume, this is, well, you could do that, of course.
But it doesn't take a nice form in Chern-Simon.
But obviously, there's always this Chern-Simons like, right? Because if you look at in principle, it looks like the kind of Chern-Simons theory, but if you look at the coefficients, they're not the degree, the structure constants are not the constants of a Lie algebra anymore. And that's good, because otherwise it wouldn't propagate modes. The Chern-Simons theory doesn't propagate anything locally, but this one does, but that's why it's kind of like. It has some of the virtues of a Chern-Simons formulation, but it doesn't involve a metric. It's very special. As I say, the remarkable thing is it's precisely that combination for which you can do this. And you can't do it for any other combination of curvature squared terms.
Okay, last question.
Is there any idea at all about how this might be embedded in M theory? Or-
No.
Nothing to do with M tubing.
I'd be the first. I'd love to be
Why
able
not?
to do that. But, as far as, yes, that's right. That's the only connection is they both involve 3 dimensions in some way. But I don't know if it has. There have been attempts to derive some of these things starting from higher dimensional gravity theories and reducing, but they don't really land up on this. They have other things. Yeah, it's a good question, but as far as I know, there's not much is known about that.
Okay. Look at the clock. I think it's time to sing, Paul.